students, we are going to discuss hybridization. Now, the hybridization concept, it is just the valence bond approach to the covalent bond formation, right? Generally, we have the from the valence bond theory, we know that the only the valence shell orbitals of an atom is involved in the bond formation, and second is that it is half filled, right student? Now if it is so, we have to then think for a while that beryllium, boron and carbon, right, these elements will have the covalency of 0, 1 and 2, but it is not so. Now student, here I have used the word covalency. Now what is covalency? Now covalency, it is the number of the half-filled orbitals, right? So before I go begin with the hybridization, I'm talking about here the word covalency. Now let's take an example of phosphorus first. You know that the phosphorus has atomic number 15. So when you will write down its configuration, right? So here we are just trying to write down its condensed form. So neon is 10, right? So we'll write it as 3s2, 3p3, right? So here the number of half-filled orbital in a first glance, it is 3, right? So here it is 3s2, 3px, 3py and 3pz to be 1, 1 and 1. So here students, the covalency here it is 3, right? And it is half filled. So here the covalency is 3. But it is not restricted till 3 because the completely filled orbital 3s2, right? It also belongs to the valence shell. From here, the excitation of electron will take place. Since it is third shell, students, it will have 3D subshell also, but that will be empty. So, what will happen? It will just get one of its electron excited to the 3D, and now you can see that here the valence shell has got half filled. How many orbital? 1, 2, 3, 4 and 5. So student, the phosphorus has extended its covalency till 5, right? So hence we can say that at the end that phosphorus has the covalency of how much? It's 5, right? Now just now I said that beryllium. Now you know that the atomic number of beryllium is 4. That means that it will have helium, this is there, and 2s2, 1s2, 2s2. Right? Here you can see that it has got 2 electrons in the s subshell and it doesn't have any half-filled atomic orbital here. Initially doesn't have any half-filled atomic orbital. Right? So here the covalency is going to be 0. Similarly, boron, you know it's 5. So here it is 2s2, 2p1. So student, here the covalency is going to be 1. That is, it is going to form the compound where it will be extending its valency maximum to 1 only. Similarly, carbon, it is 6. So it is helium, 2s2, 2p2. So students, here the covalency is how much? 2. Sorry, here it is 1s2, 2s2, then it is 2p2, but you can just say 2px and 2py, so it is 1 and 1, so it is 2 here, right? But we know that this beryllium it forms beryllium fluoride, the boron forms Bf3, right, and the carbon, it forms methane. So they have extended their valency here to 2, right, here to 3, and here to 4. So they have got the maximum covalency. Carbon has got maximum covalency of 4, right, student? So that means that the only getting half-filled atomic orbital electrons, or we can say availability of the half-filled atomic orbitals, determines the covalency of an element, right? Now, why we are coming to the concept of hybridization? Now, if only the covalent bond is formed by the overlapping of the valence shell half-filled atomic orbitals, right, students, that time the bonds which will be formed, right, uh, will be of different energy, or their enthalpy is going to be, bond enthalpy will be different. But it is not so. Let's take an example of methane. Now in the formation of methane, right, we will get the 2s subshell also involved, because here the S2, one electron will jump to the 2pz orbital, and hence we will get 4 half-filled atomic orbitals in the valence shell. Right. So that means there will be s orbital involved also in the bond formation. So the bond will be formed by the overlapping of the s orbital and the p orbital. They will be having different bond enthalpy. But it is not so. Experimentally, it is found that the 4 covalent bonds formed of by the overlapping of the atomic orbitals, they form the equivalent bond. That means the bond enthalpy of the 4CH bond in methane will be same, right? Similarly, the direction of the bond, right, is also determined, which determine the shape of the molecule. So at the end, it was, we can say, a new, or we can say the modification, or just a new concept led that the overlapping, before the overlapping takes place, students, there will be the intermixing of the atomic orbitals of equivalent energies, right, of the same atom. Now if we take an example of carbon, now carbon, right, it will be, it is having electron in its valence shell 2s 2 and 2p 2. So there will be excitation of electron from 2s subshell, right, to 2p subshell, and there will be 4 unpaired electrons, right. Now the the electrons, or with the promotion of the electron, a question can come in your mind that how the promotion of electron is taking place and from where the energy it is getting. Now students, the promotion of electron will only take place while the bond formation is about to take place, because when the two atoms will approach, you know that there is release of energy. So when there will be release of energy, that and release of energy will be used for the promotion of an electron from one subshell to the other subshell, right? So what is hybridization? Now hybridization, student, it is the intermixing of the atomic orbitals of comparable energies. There should be no large difference of the energy. There should be comparable energy, almost similar energy, right? So whenever there is an intermixing of the atomic orbitals of comparable energy, right, a new set of orbitals will be formed, which will be having same energy and the same shape, right? So we can now define the hybridization. Hope so if this is clear to you that what is covalency, students. So covalency, it is the number of the half-filled atomic orbitals in an atom, right? And the maximum covalency we can determine by just excitation of the valence shell electron to an or subshell or an orbital which is available to it and which is empty. Right? Now in the next we are going to discuss about the hybridization. Just as I said that hybridization, it is the intermixing of the atomic orbitals of an atom or an ion so that the redistribution of energy can take place, right? And the atomic orbitals which will undergo the intermixing, they should be having approximately same or comparable energies. As a result, the new set of orbitals which are formed, they will be having equivalent energy and shape. Now what is hybridization? It is the phenomena of intermixing of atomic orbitals of comparable energies of an atom or ion, right? So here let us consider, because ion will also contain the atom only at first, right? So let's just get it to be atom of comparable energy of an atom, right? To form new set of orbitals having equivalent energy and shape. The orbitals formed are called hybrid orbitals. Right, students? So, hybridization, there is an intermixing of the atomic orbitals of comparable energies. Now, that let's take an example here that if we have got the overlapping of the p orbital, s and p orbital, right? So, if this is the s orbital, right, and this is the p orbital of an atom, right? Now these two orbitals will belong to the same atom, right? In this case, what will happen when the overlap will take place? This is let it be of 2s and this is the 2p. Now students, this 2s and 2p, they belong to the same atom, right? So whenever the overlapping takes place, and it is the overlap which takes place between the same atom. Now what will happen as a result of it, we are going to get Sp, the new set of orbital which will be formed, right? This is known as the Sp orbital. Now it will be no more known as the s orbital or a p orbital spawned by the intermixing of it. So we will get the sp hybrid orbital. Yes, students. So we will get two sp hybrid orbitals. So if we are getting two orbitals intermixing, we will get two set of sp hybrid orbital, students. So here you can see that we are representing it in this way. Now the plus lobe will be always the bigger lobe. That means if we represent the single sp hybrid orbital in this way, so this will be always plus and this will be always minus. The smaller lobe is indicated by the minus sign, right? And the sp hybrid orbitals, since there were two atomic orbitals, so there will be two sp hybrid orbitals which will be formed. Right now, there are certain conditions that before the for hybridization there are conditions. Now, the first condition is that, so we'll write down the conditions. The first is that the overlapping atomic orbitals should be of comparable energy. Right? Or, sorry, not overlapping. It is the intermixing of atomic orbitals of an atom of comparable energy. That means almost nearly same. The difference should be less. The difference in energy should be very less. Right? Second is the atomic orbitals which are getting involved here, students, that belongs to the valence shell. Right? So, second is valence shell is atomic orbitals is involved, right, of the same atom. Third is promotion of electron is not a required or is not compulsory. Right? Promotion of electron is not compulsory. And the fourth point, student, here it is that all the half-filled orbital must participate in hybridization. It is also not required, right? Or we can say that it is not so that only half-filled atomic orbitals are going to overlap. It is that sometimes the completely filled orbital also participate in the hybridization, right? So we can say that it is not necessary that only half-filled orbital, even not necessary always to have half-filled half-filled orbitals involved not necessary that only half-filled orbitals involved. It can be completely filled valence shell, valence orbital, right? Valence shell orbital also. Right, students? So these are the conditions that intermixing of atomic orbitals of comparable energy will take place of the same atom, right? Second is that valence shell of that particular atom is involved. We will not get the intermixing of atomic orbital of any shell. It should be always the valence shell. Third is that the promotion of an electron is not a necessary criteria, that it has to take place. And the fourth is that it is not so that only the half-filled atomic orbitals are involved in the intermixing. It can be also so that the completely filled orbital is also getting involved, right? So we can here say that the intermixing of atomic orbitals is taking place so that the new set of orbital which is formed, the energy gets redistributed in them and they all become equivalent in energy and shape, right? Now the we can say the features of the hybridization, students. So till now you must have come to know that the hybridization leads to the, we can say, leads to the formation of the hybrid orbitals. Now the number of the hybrid orbitals will be always equal to that of the combined intermixing atomic orbital. If we have two atomic orbital intermixing, we will get two hybrid orbitals. These hybrid orbitals will be having the similar, or will have the equivalent energy, and they will be having equivalent shape, right? And the most important, student, is that why the hybridization? Because the atom which will undergo the hybridization, and then after that the bond which will be formed with the help of these hybrid orbital will be stable bonds is going to be formed, right, students? So just try to point out the characteristics of the hybridization, or the features of the hybridization, from the uh, topic which we have just covered now, right? What are the features of the hybridization, or what are the characteristics of the hybridization? Students, we have started hybridization. Now today we are going to discuss the characteristics of hybridization. Though I have asked you to point out these its characteristic, then also let's just cross check. Okay, so first one is that the hybridization, it occurs between the atomic orbitals having the equivalent energy, right? And the orbitals which will undergo the hybridization, they belong to the valence shell. The hybrid orbitals which are formed, they will be equal in number as that of the intermixing atomic orbitals, right? So the characteristics of hybridization, the first is that the hybridization of valence shell atomic orbitals of comparable energy takes place. Second is the number of hybrid orbitals formed is equal to the number of intermixing atomic orbitals. Third, student, is that the intermixing of atomic orbitals will take place only during the bond formation. That means the individual atom will not undergo hybridization until unless it is not about to form a bond, right, student? So the hybridization, or we can say that it takes place not in a isolated atoms, but it occurs only at the time of bond formation. So we can say that hybridization does not occur in isolated atoms. It occurs only during the bond formation. The fourth point, student, is that the hybrid orbitals have equivalent energy and shape. Right, students? So the hybrid orbital which will be formed will have equivalent energy and shape. That means during the hybridization, student, what has taken place? The redistribution of energy has taken place. Right? Now, the next characteristic is that the hybrid orbitals are directional. It means that is directed in a particular direction in space, right? Hence, the shape or geometry of a molecule can be predicted by knowing the hybridization. Six is the bond formed by the hybrid orbitals are more stable are more stable than the atomic orbitals, right? That means the hybridization leads to the stability of the bond, right? So these are the main characteristics of hybridization, students. So now it should be clear to you what is hybridization. It's just intermixing of atomic orbitals. An isolated atom, before undergoing the bond formation, right, according to this concept, will undergo the intermixing of the atomic orbitals of its valence shell having the comparable energy, right? And as a result, the hybrid orbitals which will be formed, they will be having the equivalent energy. Earlier the orbitals were having different energies, right? There was slight difference in the energy, but now after undergoing the intermixing, they will have the equivalent energy and shape. Now the hybrid orbitals which are formed, they will be equal in number as to that of the intermixing atomic orbitals. If the atomic orbitals intermixing are 2, the hybrid orbitals which will be formed will be also 2, right? Then next is that the hybrid orbitals, they are directional. That means they direct in a particular direction in the space, and hence by knowing the hybridization we can predict the geometry or the shape of the molecule. Now why the hybridization concept is important? Because the bond which the bond which is formed by the overlapping of the hybrid orbitals, right, is more stronger, is, or we can say is more stable than the ordinary atomic orbitals, right? Now we will take examples which will be related with the type of hybridization, that is sp3, sp2, sp. right? Now let's take the exam. Let us first consider the sp3 hybridization. Right, students. So, as the name itself is suggesting that it is sp3, that means it will involve one s atomic orbital and three p orbitals. Right. So, we will, and this sp3 hybridization is also known as the tetrahedral hybridization. Hybridization. Now, students, let us take the example of an alkane here. Right, that is a methane. So, we are taking an example of alkane. Let it be methane. Right, students? So first, here the central atom will undergo the hybridization. So here, students, central atom is carbon. So let's first write down its atomic, its electronic configuration. You know that it has got 1s2 helium, and we are writing its outermost shell configuration, that is 2s2, right? 2px, 2py, and 2pz. So it's 1, 2, 3, 4, and it will have 5 and 6, right? So this is the outermost shell configuration. Now when the hybridization will take place, right? So students, I am drawing here the hybrid table also, hybridization table. So it will get the thing more clear to you. So you can see here that a 2p subshell is half filled. Half filled means 2px is having one electron, 2py is having one electron, but 2pz is not having any electron. So how we will draw it? So we are writing here G carbon, and here we are writing it in the ground state. So here we will write down, as I said you earlier, that we are going to take the outermost shell configuration only. So here we are taking 2s and 2p. Right. So here 2s has got 2 electrons. Here it is 1 and 1. Now student, there will be, to get the 4 hydrogen atom bonded, these 2 electrons are insufficient, right? Unpaired electrons. So there will be excitation. So we will write it as excited state. So here what will happen, the 1 electron from 2s is going to jump up to the 2p subshell, so that the covalency of carbon exceeds to 4, right? So we have got here 4 unpaired electrons. Now student, according to the hybridization, now these 1 2s orbital and 3 2p orbital are going to undergo the intermixing or hybridization. So we will write down here the hybrid state, right? So student, these 4 atomic orbitals now, they will undergo the intermixing, right? And they will form, they are undergoing the sp3 hybridization, that is the intermixing of 1s, right, and 3 p orbitals are going to intermix. Now all of these will be of equivalent energy, and these 4 are known as now sp3 hybrid orbital. Now these 4 are known as sp3 hybrid orbital, right? And then the redistribution of energy has taken place, and now these 4 electrons are going to get filled up. This is sp3 hybrid orbitals. Now student, it is having sp3 hybridization. Now what is the percentage of s character here? So total orbitals which are involved is 4, and out of it only one is s orbital. So from here you can easily calculate out that sp3 hybridization has got 25% s character. Right, students? So once the hybrid orbitals are formed, the sp3 hybrid orbitals are formed, the next step is the, sorry, is the formation of methane, right? Methane molecule. So what will happen now, this sp3 hybrid orbital will getting overlap with the four hydrogen atoms. Now this, it is 1s of hydrogen atom. This is also 1s of hydrogen atom. This is also 1s of hydrogen atom, and this one is also 1s of hydrogen atom to form the sigma bond. So the methane molecule which is formed here is formed by the overlapping of the sp3 hybrid orbitals with the 1s of the hydrogen atom and result in the formation of sigma bond. Right. So if we take carbon here, this is the carbon. Its sp3 hybrid orbital. One of the sp3 hybrid orbital is this. Another is this. And this is the fourth sp3 hybrid orbital. Now the bigger lobe, as I said earlier, will be bearing the plus charge, and the smaller lobe, the right here smaller will be having the negative sign, and this is the student hydrogen atom. Here is also, this is the hydrogen atom, right? So here the shape is tetrahedral, and the bond angle will be 109 degree 28 minute, or you can write down 109.5 degree approximately, right? So it is, this is there. So this is the bigger lobe, this is the smaller lobe. The bigger lobe generally have the plus sign here. So this is there, right? And this is our tetrahedral geometry of methane. So wherever there is a sp3 hybridization, the sp3 hybrid orbitals, they just arrange themselves in such a way in the space so that they have minimum repulsion, and hence the shape which is acquired is tetrahedral, and the bond angle which come is 109 degree 28 minute.